All right, this is Mrs. Calder, and this is the lecture that we did in class in honors chemistry this week. I figured that I would give you a little recording in case you were absent one of the days and in case you weren't clear on something that we covered in the PowerPoint. So this week's lecture was on the scientific method, and we basically went through all the steps, most of which I'm sure you already knew from previous experience: problem, background, hypothesis, experiment, data, conclusion. And so we're going to kind of take a look at each of these steps and how it's important for solving our problem. So the question is the problem that we're trying to solve, and it should be something that we can test. We should write our question in such a way that we could actually do an experiment to solve that question. I gave the example in class: does steak make my dog happy? Or do dog biscuits make my dog happy? And we talked about how it could only be a valid question if we could come up with a way of measuring happiness. Maybe we're going to measure how many times the dog wags its tail, or maybe we're going to somehow measure its brain waves or something, but we would have to come up with a way to measure happiness before we could actually do an experiment. So the one we talked about in class was that Avon makes a product called Skin So Soft, and a lot of people have said that they use it as a mosquito repellent. And it's not advertised as a mosquito repellent, it's just advertised as like a moisturizer. So our question that we were going to try to answer was, is Skin So Soft an effective mosquito spray? So that was going to be our question. First thing we want to do now is get our background research. You might say, well, I know what mosquito repellent is, but we don't know much about the Skin So Soft, and you may not know a whole lot about mosquitoes. So what kind of things might we look at? We might talk to people who say it works. We might look up the ingredients and see, does it have something in common with mosquito sprays? Maybe it smells like mosquito sprays. Maybe it feels like a mosquito spray. So there could be a lot of background information that might help us to determine whether there's something in common with mosquito spray. All right, and now we come up with our possible solutions. And so that's our educated guess, our hypothesis. And we want to try to write it in such a way, a lot of times we write it in an if-then statement, where we basically say, if Skin So Soft repels mosquitoes, which is what we think, then, and then the then part is kind of the specific result that we're expecting to see in our experiment. So for example, I had suggested an experiment where he said, we're going to put a chamber, and one side we're going to spray with Skin So Soft, and the other side we won't spray, and then we'll just count mosquitoes after a certain period of time. And if Skin So Soft does indeed repel mosquitoes, then what we should find is that there'll be less mosquitoes on that side of the chamber. Somebody in class came up with a different one. What if we sprayed Skin So Soft on one person, and then we didn't spray it on another person, and then we counted after a certain amount of time how many bites each of the people had? That would also be a valid experiment, and we would know that if the person had less bites, that would tell us that indeed Skin So Soft did seem to repel mosquitoes. All right, so we're going to skip over to parts of the experiment. So the first part is our independent variable. Sometimes it's also called the manipulated variable because it's the thing that you are controlling, that you are changing. And in this case, what we would be changing was either the side that had Skin So Soft versus the side that didn't, if we were doing the experiment with the chamber, or we could have it be the person that has Skin So Soft sprayed on them versus the person that doesn't. So our independent variable is what we are going to change. And then we would have a group that receives that variable. So in the case of the chamber, the side with Skin So Soft sprayed in it, that would be our experimental group. In our person experiment, the person that had, or group that had Skin So Soft sprayed on them, they would be our experimental group. Now, in addition to our experimental group, we would have a second group called our control group. And this is sort of the group that's going to be left alone as a comparison. It'll be exactly the same as the experimental group in every way, except for the one variable that we're testing. In other words, if you just had a group of people and you sent them outside and they all had Skin So Soft on them and you measured how many bites they had, that wouldn't necessarily tell you that Skin So Soft was what caused them to have more or less bites. So by having a comparison, another group of people who don't get Skin So Soft, we can now compare the two groups and see, yes, does Skin So Soft lower our bites in comparison to the group that didn't receive it, or did they both get similar number of bites? So that's the purpose of having our control group. All right, so we had our independent variable, and our independent variable is what we changed, and we made sure that we included an experimental group that received the change and then a control group that did not. Our other variable is called the dependent variable, and that's what we're going to be looking for. It's what we're going to write down. It's sometimes called the responding variable because it is going to respond to what we changed. So in our experiment, well, we had two, but in the experiment with people, we were going to be counting or looking for the number of bytes as our data. If we had done the other experiment with the tank with one side that has Skin So Soft sprayed on it and the other side doesn't, we would be counting how many mosquitoes were hanging out on each side. And so that would be our dependent variable, what we measured. All right, and we already talked about the control group, which would be the group that's left alone, but we also need to have what we would call controlled variables. And don't get those mixed up with our control group. Controlled variables would be the things that we want to keep the same for everybody. For example, it would not be a good experiment to have people go outside in the morning with Skin So Soft on and then test my people without Skin So Soft later in the day, because now it's not controlled. That variable of time of day has now been added to the mix, and maybe there's just less mosquitoes at certain times of the day. Maybe we want to make sure all the subjects are similar in age. Somebody in class mentioned maybe we want to even make sure they're the same blood type. Make sure that it's the same age of mosquitoes. If we had all male mosquitoes in one of the groups, male mosquitoes don't even suck blood. So that would obviously affect our results. So all the things we would want to be the same for everybody, that would be our controlled variables. And then once we do that, we're now going to get our data, and we're going to write down our data and draw our conclusions. So usually when we do our data, we're going to oftentimes make a chart, and then a lot of times in our class we'll be asked to make a graph. So one thing you need to be clear on is which kind of graph are you going to use? And this is your guideline. For the most part in our class, we probably are going to use line graphs. However, here are the two main kind of graphs that we may use in class. So a line graph would be used if our data is all numbers. For example, if we had amount of fertilizer that we gave plants and then how tall they were, that would be a line graph. On the flip side though, let's say we did our mosquito experiment. We had people with Skin So Soft and without Skin So Soft, and we counted how many bites they had. That would need to be a bar graph because you really only have two groups, with Skin So Soft, without Skin So Soft. That's not a number. And so that would be an example of where we would want to make a bar graph. And so here are some examples, and for now we're just going to determine what kind of graph they would be, and we'll come back and determine what goes on the axis in a few minutes. So our first one, how many schools use iPads in Broward versus Dade County? Well, Broward and Dade County are not numbers, they're places, and so that would need to be a bar graph. Our second one, how many students wear polos versus spirit shirts on a particular Friday? Again, polo and spirit shirt, these aren't numbers, so this would need to be a bar graph. Number 3, how many milligrams of fertilizer produce the best plant growth? Okay, well, growth is probably going to be something we would measure for height, for example. So that's going to be a number, how many centimeters tall they are, or inches, or whatever. And milligrams is an amount of fertilizer. So these are both numbers. This would be a good line graph. Number 4, how distance from light correlates with photosynthesis. Well, we could say that photosynthesis could be measured, for example, let's say we were going to measure it by oxygen production. Well, oxygen production would be a number, and the distance from the light would also be a number, so this would need to be a line graph. All right, number 5, the speed at which an enzyme makes product at different pHs. Well, pH is a number, 1 through 14, and the speed at which an enzyme is making the product could be in milligrams per second or millimeters, centigrams per minute, but it would definitely also be a number, so another line graph. And finally, amount of product made as time progresses. In this case, you would have time as one axis and how much product, again, it could be grams, liters, whatever, on the other, so this would also be an example of a line graph. All right, the next thing is you can't just put whatever you want on the x versus the y. Your independent variable always goes on the x. So the thing that you have changed, what was in your control, that's your x-axis. The thing you measured, the data you collected, that's your y-axis. And I also showed you in class that if it's possible, you may want to draw a line of best fit. If pretty much your data is showing a straight line, but you have a couple of dots that are off by a little bit, try to draw a line of best fit if you can. Don't force it to be a line if it's not a line. I showed you in class that one of the graphs, the last graph we did, was actually a curve. It was making something and then it slowed down and eventually it kind of flattened out. And some people tried to force that into a line of best fit. It was more of a curve of best fit. So try to, not connect the dots, but follow the basic trend that they show. I have a couple of examples at the end. Here are 3 types of graphs sometimes we see just to show you. If you had dots that sort of followed this trend, you're not going to try to draw a straight line. Look at this one. This is obviously a curve. They don't necessarily connect the dots. They try to make it smooth, but they don't try to force it into being a straight line either. And here's another example. Our dots follow a particular trend. And this one is showing a bell curve. Sometimes you have a bar graph and you can actually see a trend there too. So hopefully that clarifies what I mean. Don't go crazy trying to make a line if it's not a line. Just try to make it something that's smooth. All right, a few more rules. Make sure you give your graph a title. Make sure that you label the axes. Some of you in class were doing that, but you were forgetting to include the units. So if you just put time, for example, and I have 1, 2, 3, 4, 5, I don't know if that's minutes, seconds, milliseconds, hours. So make sure you include your units. Technically, you're not really supposed to graph beyond your first or last data point. If you stopped recording at 100 milliliters, you really don't want to continue your line past that. Also, you don't necessarily have to start at 0. If you have a graph and the first recording number is 100 and your data goes from 100 to 150, it's okay to start your x-axis at 100 or your y-axis at 100. You do not have to start at 0, 0. And finally, make sure your spacing is proportional, meaning if you are going to graph a period of 60 seconds, you can't put the same amount of space and go 0, 10, 30, 60, and put the same amount of space between those numbers. You need to come up with a scale that's going to fit your space. Okay, I need to record 60 seconds worth of data. To fill this space, I should put it in 10s, 10, 20, 30, 40, 50, 60, or 20s, 20, 40, 60, or maybe you have enough space to do it by ones. But you come up with a scale and then you add your data. Don't just say, okay, I only have 3 numbers, 10 seconds, 30 seconds, and 60 seconds, so I'm going to equally space and do 10, 30, 60. That doesn't make any sense because you don't have even spacing between your numbers. Okay, and so let's go back to this really quick. This is where we decided what kind of graph to use. So let's go over really quick what should go on each axis this time. So we're counting how many schools, and the independent variable is the county. That's what we're changing. So Broward and Dade County should go on your X, number of schools on your Y. Here, polos versus spirit shirts is our comparison, so that's our X. The number of students would be our Y. Here, how many milligrams of fertilizer produced the growth? So the growth is what we're measuring. Fertilizer on the X, growth on the Y. How distance from light correlates with photosynthesis. We are changing the distance, that's our X. The amount of oxygen produced, or however we're measuring photosynthesis, that's our Y. And then the speed at which an enzyme makes product at different pHs. So we are changing the pH, that's our X. The speed would be our Y. And then the amount of product made over a period of time. Typically, if we're looking at something happening over a period of time, it's usually time on our X, and amount of product, what we're measuring on our Y. So make sure you know which variable goes on the X versus the Y. Alright, and then to wrap this up, the rest of it's pretty easy. Analysis and conclusions. After you've completed your experiment, you've graphed your data, you want to explain what does your data show you. And then you want to draw, accept or reject your hypothesis, and then draw conclusions about what your data showed. Last thing, quick comment. Don't say that your hypothesis was proven. I proved that fertilizer makes plants grow faster. What you want to say is your hypothesis was supported. That way you leave a little leeway for further experimentation. If we do lots and lots of experiments, our hypothesis first became a conclusion. If lots of scientists do experiments that support that conclusion, that's when we get a theory. A theory has lots and lots of support. But don't say proven, just make sure that you say supportive. And hopefully that helps you with the scientific method.